So as I mentioned, we want to know, learn now how to calculate magnetic field vector around the conductor carrying some current. And these kind of experiments were done by two scientists, Biot and Savart, and they conducted experiments on how electric current affects on permanent magnets. So we kind of create magnetic field and use permanent magnet as a detector, as some test magnet. So they came up with an equation. So it's based on experimental observations. In order, while summarizing it, they came up with an equation which describes how electric current, like different segments of this wire, create magnetic field in the space next to it. So magnetic field vector, like dB, we will mark it, at some point in space P, is associated with a length element of the wire, ds. So some small element of this wire, not whole wire, because then we need to consider take into account the shape of the wire, its length, and do integration. But now we are talking about like small element of this length element of this wire. And also, of course, we need to take into account electric current which flows through this wire. So it was shown that based on just empirical experimental observations, that the direction of magnetic field vector is always perpendicular to this length element vector, and also the unit vector r, which is directed from this small length element to the point P, where we want to calculate magnetic field. So it's kind of a unit vector of the position vector, where then absolute value of this position vector will be just distance from the length element of the wire to the point P, where we want to calculate the magnetic field. So second observations which should be taken into account is that magnitude of magnetic field is inversely proportional to the distance from this length element ds to the point P. So it reversely proportional to 1 over r squared. And another experimental result which they have shown that the magnitude of this magnetic field is also proportional to the electric current and the amplitude of the length element. So absolute value of this, of the longer element length element we take, the proportionally we increase magnetic field. However, we want at the first step to take as small elements as possible, to consider them negligibly long in comparison to the position vector r, which is defined as the distance between element ds and point P. Then also what is important in order to get this summarized final equation for the Biot-Savart law, that magnitude of magnetic field is proportional to sinus theta, and this theta is the angle between length element ds and this unit vector r, which is directed from ds to point P. So summarizing all these experimental findings, it was derived the so known Biot Savart law. And in this case, we can write that magnetic field vector is equal to mu naught divided by 4 pi times electric current times ds vector product with the unit vector r divided by r squared, which is like absolute value of position vector, and actually it's equal to distance between length element ds and a point where we calculate magnetic field. So this is the equation which describes this law, called in honor to scientists who derived this equation, Biot, Savart. So here this mu naught is a constant. Oh, excuse me?
Is it a constant? Yeah, mu naught. This is the constant, yeah, as I suppose.
Yeah, it is a constant. And it's called permeability of free space. And its value is 4 pi times 10 in the power of minus 7 Tesla times meter divided by ampere. So this is some feature of the permeability of free space, and of course later we will see that depends on the properties of the material which fills the environment where we try to calculate magnetic field. There will be some additional constant which will take into account features of the material. But so far we are dealing with vacuum, like no material which fills this environment, this space around the electric wire, like some wire with electric current. That's why we deal with free space. So this is just first step, because the next step is to calculate actually the let's say some effective resultant magnetic field vector. There will be just B created by all length segments of the wire. So far we were dealing only with one length segment, but it's like very small part of the wire. Obviously, when we need to get the total magnetic field vector in a given point P, we need to see what magnetic field vector dB will be created by each of these length segments, and then we just sum it up. So we have some integral all over the length of the electric wire. And here this integral actually is necessary to highlight that it is not just along like some linear integral along the length, but it involves vector product of length element ds and unit vector of the which defines the position vector direction. So in this case it will be mu naught times I divided by 4 pi. So these are constants, we can factor them out from integral. And here we have this vector product ds times unit vector r divided by r squared. So r squared we cannot put like factor out from integral because it will be really defined by the position of the length element ds, and it will be different for different length elements of the y. So this should be under the integral. So now we are done with this final form of effective or resultant magnetic field vector, and makes sense to try to consider some cases to practice with application of this law and calculate magnetic field vector next to different conductors. So by the way, if we come back, if we take a look on this equation, maybe like this first one before integration. So it somehow can correlate with our memory about Coulomb law, because we also have 1 over r squared, like distance between 2 points. So it gives us electric field vector as a function of 2-point charges, or just 1-point charge if we calculate just some electric field vector next to 1-point charge. And there is also proportional to 1 over r squared. However, it's really different because electric field of a point charge possess some spherical symmetry, and here it's the direction of the magnetic field vector is actually always perpendicular to the radius vector direction, because we have this vector product of the length element and the unit vector of the position vector. So that's why they will be magnetic field will look different if we have some representation of magnetic and electric field around the source. So here source is considered as this small length element with electric current I flowing through it, but in case of point charge, it will be just electric field, it will be just point charge. So let us go to another slide and consider a few examples. So let us have some system of coordinate here. Will be x, y, then let us have some conductor, and consider at some coordinate x. Actually it's minus x, because here we consider 0. Some length element ds, and we have here some point P where we want to calculate magnetic field vector. So if we have some line which connects our length element ds with the point where we want to calculate magnetic field vector, here we have unit vector r, which defines the direction. So the coordinate of point P along axis y will be A. So obviously, if our this lens element ds is directed along axis x, then we will have also electric current flowing in this direction from left to right, and the angle between the radius vector like this, which can be called as r, and the y-axis will be theta. So this angle between radius vector and vector of the length element will be theta, oh sorry, not theta, will be 2 pi minus theta. Okay, so looks like we have pretty much everything what we need. And of course, let's define, maybe before we go for calculations, let's define the direction of magnetic field. In this case, so we can use this rule of right screw thread when we twist a right thread in the direction from ds to r vector, then the movement, like translational movement of this right thread, will show us the direction of the magnetic field. And this is like feature of the vector product. So we will have magnetic field going from the, in this point P, going from the plane of the image towards us. This is our DB. And since all of, we have a straight conductor and all length segments of this conductor will possess the same orientation, then it means that we will magnetic field created by all length segments will have the same orientation as we have shown. So in this case, it will be oriented along axis z, which we don't show here, but it goes from this point of interception with axis y and x and goes just towards us, perpendicular to the plane of the image. Okay, now we can write that the vector product ds times r could be represented as absolute value of this vector product times k unit vector. K unit vector, it shows us that this result of this vector product will be oriented along axis z, so perpendicular to the plane of the image. And in this case, we can just take absolute value of the length element, which is dx, some small part of the conductor, times then absolute, like magnitude of the ds is dx, magnitude of r vector is its unit vector, so it's unity, so we don't have anything here. Then we need to multiply it by sinus of angle between ds and r, And this angle is 2 pi minus theta. Oh, sorry, it's not 2 pi. It's pi divided by 2. Somehow I made a mistake here. So it's 90 degrees minus angle theta. So here will be pi over 2 minus theta. And everything should be multiplied by unit vector k, because we need to keep the show the direction of this vector. So as a result, we can write that it will be equal to dx times cosine theta times k. Okay, so this is our vector product, and we will definitely need it because it's like part of the Biot-Savart equation. So in this case, we can write now that dB vector in this point P should be equal to like magnitude of this vector times unit vector k. So we show that this magnetic field vector is oriented along axis z, and this is equal to mu naught times I over 4 pi times dx cosine theta divided by r squared. And sure, we put here this unit vector k. So now we need to express different terms of this equation in other forms in order to make it appropriate for the integration. So first of all, let us define what will be the radius, so the distance between the length element ds and point P. So it will be r, and this is equal. So from this right triangular, we can show, so we know that the coordinate of point P along axis y is a. So in this case, r will be equal to a divided by cosinus theta, because it's like adjacent, cutted, and r is the hypotenuse of this right triangular. So also we need to define what is dx. So first, it's easier to define what is x, like coordinate of the, like position of the length element along axis x, and this will be again from this triangular. So now we have not adjacent but this opposite catet. So it will be minus a times tangent theta. So minus because it is negative coordinate of x for the particular length element which we are considering now. So it's kind of minus x. Okay, now we need dx, so it's differential of the x. So we need to take derivative of this, like to differentiate this. And dx will be equal to minus a times seconds square theta, d theta. And this is equal in more convenient form. It will be minus A times d theta divided by cosinus square theta. Okay, so what do we need to do now? We need to substitute instead of r its expression, which is shown here, and instead of dx its expression here. So let us do it on the next slide. So it will be db we will just write absolute value because we know already orientation is defined by this k unit vector k along axis z. So it will be minus mu naught I over 4 pi times, now we need to put instead of dx its expression, so it will be minus here, a times d theta over cosinus square theta. And also instead of r square, we so instead of r, so we have r square, and it's 1 over r square, so we flip over previous expression for r and takes square of this, so it will be cosinus square theta divided by a square, and everything is multiplied by cosinus theta. Okay, now what do we get? So this a and this square cancels out. Then we cancel out this cosine square and this cosine square. And eventually we get minus mu naught I over 4 pi a in the denominator times cosinus theta d theta. And now we have a final expression for integration. In order to integrate for full length, so what we need to consider? Again, here we have this system of coordinates. We have our conductor, and this is our point P, where we want to define the magnitude, or like the magnetic field vector. So if we show with these lines how they are connected with the edges of the conductor, so we have here theta 1 and theta 2. So we need to integrate from angle theta 1 initial to angle theta 2, the final. But before we do that, here is one mistake. This minus should not be here. It's minus we put here in the parentheses next to dx element. And this minus then will be here. So eventually we have minus, because otherwise minus and minus would cancel out each other. So here we initially don't have any minus. So now we can integrate, and our magnitude of the total effective magnetic field vector, which is aligned along axis z, will be equal to minus mu naught times I divided by 4 pi times a, integral from theta 1 to theta 2. And here is cosine theta d theta. So this will be mu naught times I over 4 pi a sinus theta 1 minus sinus theta 2. So this is the final equation, which will give us the effective magnetic field vector at point P created by all length elements of this conductor, straight conductor, which we consider. And what is interesting for us now is to consider case of very long conductor, and that will be the condition when x, let's say this is x1, this is x2. So x1 will be equal to minus infinity, x2 equal to infinity. So in this case, these angles, theta 1 and theta 2, will be equal to 90 degrees. So it will be, they will approach pi over 2. So in this case, if we consider this very long conductor, sinus theta minus sinus theta 2, it will be sinus pi over 2 minus sine minus pi over 2, because it kind of in the other direction angle, and this will be equal to 1 minus 1, so it will be equal to 2. So instead of this parenthesis for very long conductor, we will just use factor of 2, and this magnetic field vector for very long conductor will be equal to mu naught times I over, instead of 4, now 2 pi a. So this is equation for magnetic field vector, strength of magnetic field vector absolute value at the distance a from a very long wire with electric current I. So this is kind of a standard equation, which you should remember, because there is a high chance that you will need it for solving certain problems. So let us consider another example with calculating this magnetic field vector. So let us consider another system of coordinates. So this is y, this will be z, and here will be x. So let us have some loop circle of conductor with electric current flowing in the counterclockwise. So it will be like this, electric current. And Here we can consider one lens element, ds. Then we want to calculate magnetic field vector at the point P, which is located on axis X. And of course, its coordinate is X. So then we have this radius vector, like distance from the ds to our point P. And here is our unit vector R. So according to the rules of vector product, put this P here, the direction of this vector product ds times r will be like this. So we can translate it along this radius vector to point P. So this will be our vector dB. And since it kind of tilted, so we can consider two components of this vector. So here is some angle theta between axis x and our vector dB. That will be exactly the same angle here between the unit radius vector and axis y, theta. And now we have two components. We have dBx and dBy. So this is projections of vector dB on x and y. So first of all, let us consider this dBy. Because of the symmetry, we had a considered similar problem with electric field calculation. So because of the symmetry of this loop, we can always find another lens element which will have the same magnitude of dBy, projection of vector dB, but in opposite direction. So when we sum them up, it will be equal to 0. So that's why the resultant vector of magnetic field will be aligned in our case only along axis x and will be defined as the sum of all x-axis projections of vector dB created by each segment of this current loop. So for that, we will need to integrate. So once we define all these parameters, we need to show what will be the value of dB x. So the magnitude of vector dB will be defined by the Biot-Savart law. So it will be mu naught times I over 4 pi ds times r unit vector. Here we take absolute value because we already we know we want to get the absolute value of this like magnitude of this vector over r square, and taking this into account, it will be mu naught I over 4 pi. Here will be ds because r is unit vector over, and this r square is equal to a square plus x square. And a square is a radius of this, a is the radius of this current loop. So it is again right angle triangular. So we have adjacent catet and opposite catet, so we can calculate the hypotenuse. So here will be a squared plus x squared instead of r squared. So now we need to define what will be the projection of dB vector on axis x. So dBx will be equal to the product of the dB on cosine theta. So it will be mu naught I over 4 pi ds over a squared plus x squared times cosine theta. So now we know the dx component, and what we need to do, we need to calculate the total sum of dB x of created by each of the segments of this current loop. For this, we need to integrate, so bx, actually the magnitude of the magnetic field vector at point P will be equal to integral over the whole current loop dBx. So this is equal to mu naught times I over 4 pi integral over the whole loop ds cosinus theta over a squared plus x squared. So we don't have angle, we need to express cosine theta in terms of a and x in order to be able to integrate over the entire loop over these small elements ds. So cosine theta is nothing else as the ratio between radius of the loop A and distance from ds to point P. That will be A divided by a squared plus x squared in the power 1/2, like square root of r squared actually. So now we can substitute this in the integral instead of cosine theta and get the final expression for the integral, which should be taken. So it will be mu naught I over 4 pi. Also, we need to take into account the symmetry of the this current loop. Doesn't matter which segment we use, the distance to the point P, which is a squared plus x squared, will be the same because it's just a circle. And this point P locates on the axis which goes through the center of this circle. So that's why all like a and x could be considered as constants and taken like factor out from the integral. But in this case, we need to consider instead of cosinus theta, we put this expression. As a result, we will get a over a squared plus x squared in the power of 3/2. And finally, this integral over the loop ds. So actually, now we have only this lens element, and we integrate all over the circle. And that means that we eventually should get the length of the loop, the length of the circle. So it will be 2 pi times a times radius of the loop. So let's go to another slide and write again the expression for the magnetic field in the point P. It will be mu naught I over 4 pi a over a squared plus x squared in the power of 3/2 times 2 pi a. So this is, instead of our integral, it's actual length of our loop. And final equation will be mu naught I times a squared divided by 2 pi. Oh, sorry, not 2 pi, just 2 pi is in the numerator also. So it will be just 2 times a squared plus x squared in the power of 3/2. So this is the final equation. And we need to consider this at two different conditions. So let's say x is equal to 0. So when we want to calculate magnetic field just in the center of this loop, locate this point P, then we consider that x is equal to 0, and then Vx will be equal to mu naught times I divided by 2a. And another condition which we want to consider, that x is much larger than a. So actually this point P is located very far from this current loop. So in that case, we can neglect with a square in the denominator, like here, because it will be much smaller than x squared, and bx will be equal to mu naught I a squared over 3x cubed. So these are also important equations which could be quite often used for solving different problems, depends on the conditions. So with this, I think we finish our lecture. We will continue on Wednesday with the magnetic force between two parallel conductors, and that includes the consideration of this Ampere's, so-called Ampere's law. But this will be another topic, so we will consider conductor in the field of magnetic field, which is created by the another long wire, and that will give us the force per unit length of these two wires, how much they interact, either attract each other or repel, depends on the orientation of electric currents in these wires with respect to each other. Either they flow in the same direction or in the opposite directions. Okay, thank you very much for attention. Any questions?
Thank you, Prof. No questions, thanks.
Okay, then have a good evening and see you on Wednesday. Don't forget to come to lectures.
Yeah. Goodbye, Prof. Have a nice day.
You
Bye-bye.
too.
Thank you. Goodbye.
Bye.